Welcome to this talk. I'm going to present our work, Beyond the Tests, Program Vulnerability Repair via Crash Constraint Extraction. This is a joint work between National University of Singapore and Peking University. As all of us may know, software vulnerability is a weakness which can be exploited by attackers to steal our important information or crash the software system. According to a study, there were more than 20,000 vulnerabilities reported in 2019. However, there is usually a long delay in publishing vulnerability patches. On average, it took around 3 months to fix a vulnerability. Even for critical vulnerabilities, it also took around 50 days. Such delay will expose the software system under the threat from malicious attackers. Automated program repair is a technique that can automatically fix software bugs. Existing repair systems usually take as input a buggy program and a set of test cases, including failing tests and passing tests. In the repair process, the tests serve as a program specification. The repair goal is to produce a patched program such that the patched program can pass all the given tests. However, test-driven program repair has a problem. The specification of the program demonstrated via test case are usually incomplete specification. The examples can only specify parts of the expected behavior of the program. Specifically, the patched program may fix the bug on the given test cases, but it may still be buggy on the input outside the given test suite. To solve this problem, we propose a new repair system based on abstracting the failing test cases. When a vulnerability was detected, people usually report an exploit that can trigger this vulnerability. Unfortunately, there could be many unknown test cases that can trigger the same vulnerability. To completely fix this bug, our insight is that we can first abstract the concrete exploit to an abstracted representation of the vulnerability. In this work, we formulate the vulnerability as a violation of constraint, and then we use the constraint to guide our repair process. Our repair goal is to change the program to satisfy the constraint. Once the repaired program satisfies the constraint, we will ensure that we completely fix this bug. First of all, we propose a template-based constraint extraction. We think that many of the vulnerability can be formalized as a violation of constraint. For instance, a buffer overflow can be formalized as a violation of buffer access is less than buffer base plus buffer size. An integer overflow corresponds to a constraint A operator B must be greater than the minimal number and less than the maximal number. Let's see a simple example of a buffer overflow that happens at line 8. The size of buffer row is set as len, and the bug is triggered by an exploit that set the variable len as 256 and the variable nrow, which is the index to access this buffer, also as 256. The concrete buggy state is row 256, which is out-of-bound access. The violated constraint is that nrow is less than the size of row. Now let me give more detail on how to generate the abstracted constraint. Similar with sanitizer, our concrete state abstraction consists of two components: compilation time instrumentation and runtime abstraction. At the compilation time, when allocating memory, we associate metadata with the allocated memory space. The metadata record the reference name of a buffer size, which is len in this example. It also records the reference name of the buffer base, which is rows in this example. At runtime, when a bug is detected, we refer to the metadata associated with the overflowed buffer and produce the corresponding constraint. With the abstracted constraint, I'm going to show how we use this constraint to generate patches. The first step of program repair is to determine the location to introduce patches. Since the fixed location is usually different from the buggy location, and the constraint is produced at the buggy location, so our step is to backward propagate the constraint from the buggy location to fixed location. Basically, we are solving a whole triple given the crash-free constraint at the buggy location and a program P between fixed location and buggy location. We generate CFC prime at the fixed location. To solve this problem, we follow an existing paper and use forward symbolic quotient to calculate the Vicky separate condition. I'm going to skip the technical details here and show it using a simple example. In this example, suppose the fixed location is at line 2 and the buggy location is at line 6, and the CFC at line 6 is y is greater than 5. At line 2, live variables x and I will be set as a symbolic variable. By performing symbolic quotient along with two paths, the if path and the else path, we will generate the Vicky separate condition at the fixed location, which is x plus 1 is greater than 5 or x minus 1 is greater than 5. To generate a patch at the fixed location, we need to modify the expression to ensure CFC is satisfied after applying the patch. If CFC prime is satisfied, then CFC will be satisfied. Formally, we are going to solve a second-order formula. We synthesize a second-order expression f using the live variable at the fixed location and replace the existing expression with the newly synthesized expression f such that CFC can be satisfied. We solve this formula using a counterexample guided second-order program synthesis. I'm going to skip the details of synthesis procedure here. If you are interested, we can talk later. Combining those components together, we implement our idea in a tool called ExtractFix. Given the filling test and a buggy program, we first extract the constraint using a template-based approach. With the extracted constraint and the buggy information, we implement a dependency-based fixed locator to determine the candidate fixed location. We implemented the propagation engine on top of Clay symbolic quotient engine and built our synthesizer based on these three. Finally, the generated patch will be verified using the given exploit and sent to developers for verification. ExtractFix on 30 real-world CVEs and compared it with existing repair tool Profit, Angelix, and FixToFit. Profit is a search-based repair tool, Angelix is a semantic-based repair tool. FixToFit is also designed to elevate the overfitting issue by generating more test cases. This table shows the number of correct and plausible patches generated by each tool. The evaluation results show that ExtractFix generates more plausible patches than all the other existing repair techniques, and it also generates more correct patches. Specifically, ExtractFix generates 16 correct patches, while the other tools only generate 2 or 4 correct patches. They prone to generate overfitted patches because they are test-driven program repair techniques. There were a lot of reported vulnerabilities each year, and there is usually a long delay in publishing patches. We propose a new repair technique based on extracted constraint to repair vulnerabilities. We implement a tool called ExtractFix and evaluate on real CVEs. We show that we can produce more correct patches than existing tools. Thank you.